Imagine everything you thought you knew about dinosaurs was wrong. That familiar roar? That lumbering giant you picture? Tonight, we're not just looking at the past, we're rewriting it. Get ready to unearth the hidden truths about those ancient behemoths, the ones you thought you had all figured out. You might picture a world dominated by titans, where every creature casts a shadow long enough to swallow a minivan. But the reality? It's a far stranger, far more diverse tapestry than you've ever been told. You're about to have your mind blown. Or perhaps, if a real dinosaur suddenly appeared right now, you probably wouldn't survive this intellectual journey, let alone the physical one. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Now, dim the lights and let's ease into tonight's journey together. You stride through a dense, primeval forest, the air thick with the scent of damp earth and cycads. Every rustle in the ferns makes you jump, your modern brain instinctively conjuring images of a monstrous carnivore, jaws dripping, eyes fixed on you like a juicy bipedal snack. It's a classic image, isn't it? The towering Brachiosaurus munching on treetops, the fearsome Tyrannosaurus Rex roaring through the jungle. We've been fed this diet of giants for so long, through movies, books, even the very toys we played with as kids. Every dinosaur seemed to be an ecological heavyweight, tipping the scales at multiple tons, making our modern elephants look like overgrown poodles. But here's the kicker, the first big myth we're deflating tonight. Not all dinosaurs were massive, not by a long shot. You see, the fossil record, that intricate whisper of life from millions of years ago, tells a much richer story. For every Argentinosaurus, a beast so huge it makes a double-decker bus look like a matchbox car, there were dozens, if not hundreds, of species the size of a turkey, a badger, or even a pigeon. Take Compsognathus, for instance. You might remember it from a certain dinosaur-themed movie, Scurrying in Packs. This little guy was no bigger than a chicken, maybe a bit longer with its tail, but certainly not something you'd run screaming from unless you had an irrational fear of feathery poultry. Or consider Microraptor, a tiny four-winged dinosaur, barely larger than a crow, flitting through the trees. These smaller species were crucial to their ecosystems, filling niches that the giants simply couldn't. They were the busybody scavengers, the quick-footed insectivores, the silent lurkers in the undergrowth that escaped the notice of the bigger predators. It's like imagining modern Africa and only focusing on lions and elephants, completely ignoring the gazelles, meerkats, and countless birds that make the savannah truly alive. One mainstream historical fact we often overlook is just how diverse the Mesozoic Era truly was, spanning over 180 million years and encompassing a staggering array of climates and environments. Within that vast time frame, dinosaurs adapted to nearly every conceivable ecological role. From the deep forests to the open plains, from arid regions to lush wetlands, they evolved an incredible range of sizes and forms, far beyond our popular giant-centric view. It's a bit like assuming all mammals today are either whales or elephants, forgetting about the shrews and bats that make up the vast majority of mammalian species. Now, for a quirky tidbit. Some scientists propose that the very smallest dinosaurs, particularly the feathered ones, might have occupied niches very similar to modern birds, perhaps even being excellent climbers or spending significant time in trees. Imagine a tiny, scaled-down Archaeopteryx hopping from branch to branch, its little claws gripping the bark, perhaps even building nests. This idea challenges the traditional image of dinosaurs as ground-dwelling giants and paints a picture of a much more dynamic, three-dimensional ecosystem. Historians still argue whether the perceived rarity of small dinosaur fossils is purely a taphonomic bias, meaning smaller, more delicate bones are less likely to survive the ravages of time and fossilization, or if it genuinely reflects a lower population density compared to their larger counterparts. It's a chicken and egg scenario, or perhaps more accurately, a Compsognathus and fossil record scenario. Either way, the evidence for a thriving ecosystem of pint-sized prehistoric creatures is growing, constantly reshaping our understanding of what it meant to be a dinosaur. So, next time you picture a dinosaur, don't just see a mountain of scales and teeth. Remember the little guys, the silent majority, darting through the undergrowth, just trying to make a living in a world of giants. They were there, just as much a part of the Mesozoic tapestry as their colossal cousins, perhaps even more so in sheer numbers. You continue your trek, the ground now feeling a little less menacing, perhaps even a bit more nuanced. The air still carries that earthy, ancient scent, but now you're picturing the tiny rustles and movements, not just the thunderous ones. As you pause by a massive, fossilized tree trunk, imagining the creatures that once lived here, another common image probably pops into your head: the mighty hunter. You see a T-Rex in your mind's eye, a perfectly honed killing machine, forever locked in mortal combat with a noble herbivore. It's a compelling narrative, a prehistoric drama playing out on a grand scale. We've been taught to see these magnificent predators as the ultimate apex hunters, stalking their prey with cunning and ferocity, never missing a meal, never resorting to anything less than a clean kill. But here's the next myth we're going to dismantle. Many dinosaurs, even the big ones, weren't just apex predators. They were also enthusiastic scavengers. It's a less glamorous image, isn't it? Picture that same T-Rex, not roaring triumphantly over a freshly downed Triceratops, but instead nose deep in the putrid remains of a several-day-old carcass, fending off smaller, equally opportunistic scavengers. It's not quite the Hollywood blockbuster scene, but it's far more likely to be closer to the truth. In any robust ecosystem, scavenging is an absolutely vital role, ensuring that no energy goes to waste and that nutrients are recycled efficiently. Why expend massive amounts of energy chasing down a live, potentially dangerous meal when a perfectly good, already dead one is just lying there, ripe for the picking? It's the ultimate prehistoric fast food, no cooking required. Think about modern ecosystems. Lions, those majestic symbols of the African savanna, will readily steal kills from hyenas or even other lion prides if the opportunity arises. They don't have a rigid moral code about honor in hunting. They have a survival instinct. Vultures, hyenas, jackals, they all play crucial roles in cleaning up the landscape. It's highly improbable that the Mesozoic world, with its enormous populations of large animals, lacked its own dedicated cleanup crew. And it's even more improbable that the big carnivores would pass up a free meal. The energy expenditure of hunting is immense. A sustained chase, a violent struggle, the risk of injury from a desperate prey animal, it's all avoided if you can simply waltz up to a pre-existing buffet. One mainstream historical fact supporting this idea comes from the very anatomy of some large theropods. Take T-Rex again. Its enormous olfactory bulbs, suggesting an incredibly keen sense of smell, are more indicative of an animal designed to sniff out decaying carcasses from miles away, rather than a purely visual hunter. Its massive teeth, while capable of crushing bone, might also be excellent for tearing through tough hide and getting at marrow, a common scavenging behavior. While it certainly possessed the strength and weaponry to hunt, these anatomical features strongly suggest a dual role. It's like a modern grizzly bear, perfectly capable of catching salmon or hunting elk calves, but equally happy to gorge on berries or, yes, scavenge a deer carcass left by a wolf pack. Now for a quirky tidbit. Some paleontologists have hypothesized that the sheer size of some sauropods, the long-necked herbivores, might have meant that when one died, it provided such an enormous amount of carrion that it could sustain an entire ecosystem of scavengers for weeks, even months. Imagine a veritable dinosaur deli scattered across the landscape after a particularly large Patagotitan finally shuffled off its mortal coil. This would have been an irresistible siren song for any opportunistic carnivore or specialized scavenger. Historians still argue whether the presence of healed bite marks on fossilized bones indicates active predation or post-mortem scavenging. It's often tough to definitively tell if the bite happened when the animal was alive and struggling, or if the predator simply stumbled upon an already deceased individual. The line between predator and scavenger, it seems, was as blurry for dinosaurs as it is for many large carnivores today. So, next time you envision a T-Rex, don't just see a fearsome hunter, see also a pragmatic opportunist, perhaps with a slightly cheesy grin heading straight to the free lunch. You ease deeper into the ancient quiet, the scent of earth and time now almost comforting. As you settle against the rough bark of a towering conifer, your mind inevitably wanders to the sheer brawn of these creatures. We often picture dinosaurs as magnificent, powerful beasts, yes, but also as rather simple-minded. The prevailing image, burned into our collective consciousness, is that of a magnificent body housing a brain no bigger than a walnut, a creature driven purely by instinct, incapable of complex thoughts or nuanced behavior. This perception often places them low on the intelligence totem pole, mere reptilian brutes in a world of raw power. But here's the next myth we're gently setting aside. Dinosaurs were not necessarily dumb. Many exhibited surprisingly complex behaviors and intelligence. Forget the lumbering, brain-dead monsters of old B-movies. The fossil record, combined with modern analyses of brain endocasts, the internal molds of fossilized skulls that give us an idea of brain size and structure, reveals a much more sophisticated picture. While it's true that some of the earliest interpretations exaggerated their lack of intelligence, leading to the rather uncharitable, dim-witted dinosaur stereotype, we now understand that many species possessed brains far more capable than previously imagined. Consider the notion of social behavior. Evidence suggests that many dinosaur species lived in herds or packs. Think about the massive bone beds discovered, containing hundreds or even thousands of individuals of the same species, like Maiasaura, the good mother lizard. These sites strongly imply complex social structures, perhaps even cooperative nesting and rearing of young. If you're living in a group, you need communication, recognition, and some level of social cohesion. That's not the domain of a simple automaton. You're talking about interactions, hierarchies, and perhaps even forms of teaching or learning, however rudimentary. It's a far cry from a solitary, unthinking beast. One mainstream historical fact that supports dinosaur intelligence is the discovery of evidence for parental care. The Maiasaura nesting sites, for example, show repeated nesting in the same areas over generations, with juveniles and even eggs found in various stages of development. The nests themselves indicate that adults would return to feed and protect their young, which were too large to have been simply left to fend for themselves immediately after hatching. This level of commitment to offspring, extending beyond merely laying eggs and moving on, requires a degree of parental instinct and perhaps rudimentary emotional bonds. It's a behavior that demands more than just a pea-sized brain. Now for a quirky tidbit. Some paleontologists have speculated about the potential for tool use in certain highly intelligent, dexterous dinosaurs. While no definitive fossilized tools have been found attributed to dinosaurs, aside from birds, which are, after all, dinosaurs, the idea isn't entirely far-fetched for species with grasping forelimbs and a relatively large brain-to-body ratio. Imagine a cunning Deinonychus using a strategically placed rock to gain access to a hard-to-reach nest, or perhaps even a primitive form of cooperative hunting that involved environmental manipulation. It's certainly more captivating than just envisioning them bashing into things. Historians still argue whether the apparent correlation between larger brain size and more complex social structures in dinosaurs is a direct cause and effect relationship or simply a parallel evolutionary trend. It's tough to measure intelligence directly from fossils, obviously, but the increasing evidence for group living, migration, and sustained parental care strongly tilts the scales away from the dumb dinosaur narrative. So, the next time you picture a dinosaur, don't just see the muscle and the scales. Imagine a creature with perhaps a spark of cunning in its eye, navigating a complex world with his family or pack, and perhaps, in its own unique way, thinking. The air grows warmer now, almost humid, as you push through a tangle of prehistoric ferns, the fronds brushing against your face. You're beginning to see this ancient world with new eyes, not just as a backdrop for giants, but as a vibrant, complex tapestry of life. And speaking of vibrancy, let's talk about how these creatures actually looked. For decades, when you imagined the dinosaur, you pictured something scaly, perhaps green or gray, essentially a giant lizard. Think of the classic portrayals: smooth, pebbly skin, much like a crocodile or a Komodo dragon. This image of the dinosaur as merely a supersized reptile is deeply ingrained. But here's the next significant myth we're about to pluck apart. Dinosaurs weren't just covered in scales. Many, in fact, sported a dazzling array of feathers. This might come as a bit of a shock, especially if your primary exposure to dinosaurs is still through older media. The discovery of feathered dinosaurs is one of the most revolutionary paleontological findings of the last few decades, fundamentally reshaping our understanding of dinosaur appearance, behavior, and their evolutionary lineage. It started with incredible fossil finds from China, perfectly preserved in fine-grained sediments, showing not just bones, but clear impressions of fluffy down, intricate filaments, and even fully formed feathers. Imagine a Velociraptor, not the sleek, scaly terror from the movies, but something more akin to a giant predatory bird, covered in a shaggy coat of proto-feathers, perhaps even with colorful plumes on its arms and tail. Or a Dilong Paradoxus, an early tyrannosauroid, sporting a fuzzy, insulating layer that would make it look more like a feathery badger than a reptilian terror. These weren't just isolated cases. The evidence has mounted to suggest that feathers were far more widespread among dinosaurs than scales, particularly among the theropods, the group that includes T-Rex and birds. It's believed that feathers initially evolved not for flight, but for insulation, display, or even camouflage, much like fur on mammals. You're literally re-feathering your entire mental picture of the Mesozoic. One mainstream historical fact that underscores the importance of these discoveries is the confirmation of the direct evolutionary link between dinosaurs and girds. The presence of feathers on dinosaurs provided irrefutable evidence, bridging the gap between ancient reptiles and modern avians. It means that when you see a pigeon strutting through the park, you're looking at a living dinosaur, a direct descendant of those ancient giants. It's a connection that would have seemed outlandish just a few decades ago, but now it's a cornerstone of evolutionary biology. The terrible lizards never truly vanished. They simply took to the skies, evolved beaks, and started singing.
Now for a quirky tidbit. Some scientists have even mused about the potential for iridescent feathers on certain dinosaur species, much like those found on hummingbirds or peacocks today. Imagine a male Caudipatrix, a small bird-like dinosaur, fanning out its tail feathers in a shimmering display of greens and blues to attract a mate. This adds an entirely new dimension to their courtship rituals and social interactions, painting a picture far more vibrant and visually spectacular than the drab reptilian forms we once envisioned. Historians still argue whether all dinosaurs, even the largest sauropods or armored dinosaurs, possessed some form of protofeathers at an earlier evolutionary stage, perhaps as fuzzy hatchlings, before losing them as they grew larger and no longer needed the insulation. It's a fascinating debate that challenges us to consider feathers not as a bird-specific trait, but as a truly ancient dinosaurian innovation. So the next time you dream of dinosaurs, don't just see scales. Imagine a world of vibrant, feathery creatures, some small and delicate, others massive and imposing, all part of a lineage that never truly ended.
The air now feels lighter, almost carrying the scent of distant water as you emerge from the feathered canopy into a more open space. You scan the horizon, your modern eyes trying to pierce the ancient gloom. And inevitably, your thoughts turn to the most iconic predator of all time, Tyrannosaurus Rex. And with T-Rex comes the classic movie scene, the one where the massive beast can only see you if you move. It's an incredibly potent image, designed to build suspense, to make you hold your breath and freeze, believing that your very immobility is your shield. This depiction of T-Rex with incredibly poor eyesight, relying solely on motion detection, is firmly embedded in popular culture. But here's the next myth we're going to dissect. The T-Rex did not have terrible vision. In fact, it likely had excellent, perhaps even stereoscopic, sight. Forget the idea of a giant lumbering beast bumping into trees if you stood still. The reality, as revealed by detailed studies of T-Rex skull structures and brain endocasts, suggests a creature with highly developed senses, particularly its vision. The orbits, eye sockets of Tyrannosaurus Rex are positioned in a way that suggests a significant degree of binocular vision, meaning its eyes faced forward to a greater extent than many other dinosaurs. Think of a hawk or an eagle. Their forward-facing eyes give them superb depth perception, crucial for pinpointing prey from a distance. A T-Rex with forward-facing eyes would have had an overlap in its field of view, allowing it to accurately judge distances, a vital skill for any predator, whether hunting or scavenging. It's often compared to the vision of a modern-day raptor, like an eagle, but on a much grander scale. Imagine this colossal predator not just seeing movement, but clearly discerning the texture of your shirt, the slight tremor in your hand, the way your breath hitches in your chest, all from a considerable distance. This means that freezing wouldn't have saved you. It might have just made you an easier target to pinpoint. The idea that you could simply stand motionless and become invisible to a T-Rex is a comforting thought, a narrative device designed for thrill. But scientifically, it's about as likely as riding a unicorn through the Cretaceous. One mainstream historical fact that supports T-Rex's keen vision comes from studying the optic lobes in its brain. While we don't have the actual brain, endocasts show that the areas of the brain dedicated to processing visual information were quite large, indicating that vision was a dominant sense for the animal. This aligns with its predatory lifestyle. A hunter needs good eyes to spot, track, and ultimately ambush or pursue its prey. It's a fundamental aspect of how most large carnivores operate. Now for a quirky tidbit. Some paleontologists have even suggested that T-Rex might have had color vision, allowing it to perceive the world in a rich spectrum, much like humans do. While definitively proving color vision from fossils is difficult, the presence of certain types of cones in the eyes of its avian relatives, birds, makes it a plausible hypothesis. Imagine a T-Rex not just seeing shades of gray, but a vibrant, colorful world, perhaps even using color in its own displays or to distinguish prey from its environment. Historians still argue whether T-Rex was primarily an active pursuit predator, relying on its strong legs and sharp eyesight for long chases, or more of an ambush predator, using its vision to carefully select targets before a powerful short burst of speed. Regardless of its specific hunting strategy, the evidence points overwhelmingly towards a highly visual animal, far from the nearsighted behemoth of cinematic legend. So, the next time you envision a T-Rex, don't just see a blind brute. See a creature with piercing, intelligent eyes, calculating distances and assessing threats long before you even know it's there. As you move forward, the distinct scent of pine and damp earth gives way to something drier, more open, hinting at plains stretching out to a distant horizon. You've just dispelled some significant myths about the dominant figures of the Mesozoic, the dinosaurs themselves. But what about the other creatures sharing this ancient world? Our mental image is often one of dinosaur supremacy, a time when mammals were relegated to the shadows, tiny, shrew-like creatures scurrying underfoot, barely surviving, certainly not thriving. It's a picture of an age where dinosaurs ruled unchallenged, and mammals were just patiently waiting their turn, meek and insignificant. But here's the next myth we're going to overturn. Mammals didn't just hide and barely survive during the age of dinosaurs. They were surprisingly diverse and, in their own way, thrived. Forget the singular image of a generic rat-like creature constantly on the run. The Mesozoic Era, lasting for over 180 million years, offered ample time and opportunity for mammals to diversify and occupy a surprising array of ecological niches. While it's true they didn't achieve the massive sizes of many dinosaurs, they certainly weren't confined to a single, marginalized role. The fossil record, especially from recent discoveries, has revealed an astonishing variety of mammalian forms existing alongside dinosaurs. You had early versions of creatures that resembled modern-day moles, burrowing underground to escape predators and find food. There were agile, squirrel-like mammals scampering through trees, perhaps feeding on nuts and insects, much like their modern counterparts. Some were even semi-aquatic, reminiscent of otters or beavers, diving into ancient rivers and lakes to hunt for fish or crustaceans. We found fossils of mammalian predators, not massive ones, but certainly capable of hunting smaller prey, including baby dinosaurs or dinosaur eggs. Imagine a small, badger-like creature cleverly raiding a dinosaur nest, snatching a nutritious egg under the cover of darkness. It paints a much more dynamic picture than just a world of giants. One mainstream historical fact that highlights this mammalian diversity is the discovery of Castorocauda, an early Jurassic mammal that was remarkably specialized for an aquatic lifestyle, complete with a flattened tail and adaptations for swimming. This find completely reshaped our understanding of mammalian evolution, showing that these creatures were already exploring diverse ecological roles tens of millions of years before the end of the dinosaurs. It demonstrates that mammals weren't simply biding their time, they were actively evolving and adapting to their environment, carving out their own unique places within the dinosaur-dominated world. Now for a quirky tidbit. Paleontologists even uncovered Repenomamus giganticus, a badger-sized mammal from the early Cretaceous period, whose fossilized stomach contents included the remains of a juvenile Pterosaurus, a small horned dinosaur. This provides direct evidence that some Mesozoic mammals were not just insectivores or scavengers, but active predators of small dinosaurs. It's a remarkable reversal of the usual predator-prey dynamic we so often assume for this era, and it certainly dispatches the idea of mammals being exclusively meek and insignificant. Historians still argue whether the evolutionary pressure exerted by the presence of large dinosaurs ultimately spurred the diversification and specialization of mammals into smaller niche roles, or if mammalian evolution was largely independent, following its own internal trajectory. It's a fascinating chicken and egg scenario for the Mesozoic. Regardless, the evidence is clear. The age of dinosaurs was also, in its own quieter way, a burgeoning age of mammals, laying the groundwork for their eventual explosion in diversity after the KPG extinction event. So next time you think of the Mesozoic, don't just see the colossal reptiles. Imagine the intricate, bustling world beneath their feet, teeming with a surprising variety of furry, scuttling, and even swimming mammals, bravely coexisting with their giant overlords. You find yourself walking along what feels like an ancient riverbed. The smooth, worn stones whispering tales of vanished giants. As you continue to shed old assumptions, one name often surfaces as the poster child for paleontological confusion: Brontosaurus. For generations, many of us were taught that Brontosaurus never actually existed, that it was a mistake, a misidentification, a dinosaur that was, in essence, undiscovered. It was the classic example trotted out to show how science corrects itself, but also how readily accepted facts can be overturned. This notion that Brontosaurus was a phantom, forever relegated to the realm of myth, is deeply entrenched in our collective consciousness. But here's the next myth we're going to happily overturn. The Brontosaurus is back. After decades of being considered invalid, new research suggests it was a distinct genus after all. Yes, you heard that right. The thunder lizard that graced so many childhood books and plastic toy sets has made a triumphant return to the scientific stage. The story of Brontosaurus is a fascinating saga of scientific discovery, rivalry, and reevaluation. It begins in the late 19th century, during the Bone Wars, a period of intense, often ruthless competition between paleontologists Othniel Charles Marsh and Edward Drinker Cope. Marsh described Apatosaurus in 1877. Then, in 1879, he described another, more complete skeleton, which he named Brontosaurus excelsus. The Brontosaurus specimen was indeed more robust and impressive, leading to its popular appeal. However, a little over 2 decades later, in 1903, Elmer Riggs concluded that Brontosaurus was so similar to Apatosaurus that it should be considered the same genus, just a different species. Because Apatosaurus was named first by the rules of scientific nomenclature, Brontosaurus became a junior synonym and was thus invalidated. It was a classic case of first come, first served. For over a century, this was the accepted wisdom. There was Apatosaurus, and the famous Brontosaurus was merely a mislabeled Apatosaurus. Fast forward to 2015, and a comprehensive, painstaking study meticulously examining dozens of sauropod specimens from Apatosaurus, Brontosaurus, and related genera was published. This study, led by Emmanuel Chope, Octavio Mateos, and Roger Benson, used sophisticated statistical analyses to compare hundreds of skeletal features. Their conclusion? The differences between Apatosaurus and Brontosaurus were significantly enough to warrant Brontosaurus being re-established as its own distinct genus. It was a scientific mic drop, echoing through the halls of museums and universities worldwide. The Brontosaurus was a real dinosaur after all, just one that had been mistaken for its cousin for a very long time. One mainstream historical fact that highlights this rediscovery is the very nature of scientific nomenclature, specifically the principle of priority. While Apatosaurus had priority, the 2015 study argued that the morphological distinctions between Apatosaurus and the specimens originally designated as Brontosaurus were sufficiently clear and consistent to justify Brontosaurus being reinstated as its own distinct genus.
It's a testament to how scientific understanding evolves, constantly refining classifications as new data and analytical methods become available. Now for a quirky tidbit. The common perception of Brontosaurus as having a somewhat generic, vaguely reptilian head was often due to museums sometimes using the wrong skull for their mounted skeletons, often a more generic camerosaurid head, simply because a Brontosaurus skull wasn't found with the original postcranial skeleton. So not only was the name invalid, but the popular image of the dinosaur itself was often a chimera. The corrected Brontosaurus head is actually much more slender and horse-like. Historians still argue whether the initial lumping of Brontosaurus into Apatosaurus was a result of genuine scientific conservatism or perhaps influenced by the competitive pressures of the Bone Wars. It's a fascinating look into the human element of scientific discovery. Regardless, the Brontosaurus is back, stomping its way back into our hearts and textbooks, reminding us that even the most established scientific facts can be subject to revision and rediscovery.
The air shifts again, carrying a faint, distant whisper of the familiar, like the rustle of leaves in a modern park. You've journeyed through the deep past, challenging notions of dinosaur size, diet, intelligence, and even their feathery appearance. And now, having just welcomed back the Brontosaurus, it's time to tackle perhaps the most fundamental myth of all, the complete disappearance of dinosaurs. We're all taught that they went extinct, wiped out by a cataclysmic event some 66 million years ago, leaving behind only their fossilized bones. It's the ultimate ending, a chapter closed, a clean slate for the rise of mammals. But here's the biggest, most mind-bending myth we're going to explode tonight. Dinosaurs are not all extinct. In fact, you see their direct descendants almost every single day. This is where the story gets truly fascinating, where the ancient past seamlessly merges with the vibrant present. The widespread belief that every single dinosaur perished is only half the story, and the less exciting half at that. The truth is, a specific lineage of dinosaurs not only survived the KPG extinction event that wiped out their non-avian relatives, but flourished, diversified, and adapted to become one of the most successful groups of vertebrates on the planet today. You guessed it, birds are dinosaurs. This isn't just a quirky theory or a fringe idea. It's a firmly established scientific consensus, a cornerstone of modern evolutionary biology. Paleontologists and biologists now overwhelmingly agree that birds are direct descendants of small, feathered, carnivorous dinosaurs known as Maniraptor and theropods. Think of them as the last surviving branch of the dinosaur family tree. When you watch a robin hop across your lawn, a hawk circle overhead, or a duck paddle serenely on a pond, you are observing living dinosaurs, evolved and adapted over tens of millions of years. The evidence for this connection is overwhelming and comes from multiple lines of inquiry. We've found countless fossil intermediates, often referred to as dino birds, that show a mosaic of both reptilian, dinosaurian, and avian features. Archaeopteryx, with its feathers and wings, but also teeth and a long bony tail, is perhaps the most famous example, acting as a perfect bridge. But there are many others, like Confuciusornis or Jeholarnus, which further flesh out this evolutionary journey, demonstrating how features like flight, beaks, and fused bones gradually developed within a dinosaurian lineage. The skeletal similarities between birds and their theropod ancestors are striking, from their hollow bones to their unique lung structures and even the way they lay eggs. One mainstream historical fact that clinches this argument is the presence of the furcula, or wishbone, in both modern birds and many non-avian dinosaurs, particularly theropods. This seemingly small skeletal element, formed from the fusion of two clavicles, is a unique adaptation related to the powerful flight muscles in birds. Its discovery in dinosaurs like Velociraptor and T-Rex provided a strong anatomical link, further
further solidifying the evolutionary connection. It's a key piece of the puzzle that shows the direct lineage. Now for a quirky tidbit. Next time you're having chicken for dinner, consider this. You're essentially eating a direct descendant of the dinosaurs. It's a thought that adds a whole new dimension to your meal, turning a common culinary experience into a moment of profound evolutionary reflection. Suddenly, your plate isn't just chicken and potatoes, it's a living link to the Mesozoic. And remember that crocodile dunk sunscreen from earlier? It's a silly thought, but it reminds us that while birds are dinosaurs, they've certainly evolved away from some of their ancestors' stranger habits. Historians still argue whether the term dinosaur should be expanded to formally include all birds, or if non-avian dinosaur and avian dinosaur are sufficient to distinguish between the extinct groups and their living descendants. It's a debate about classification and terminology, but the underlying biological reality remains undisputed. Birds are, taxonomically speaking, dinosaurs. So, as you drift off tonight, remember that the age of dinosaurs didn't end. It simply took to the skies, evolved, and continued to sing its ancient song in a million different forms around the world.
The air around you feels almost charged now, carrying the faint scent of sulfur, a distant echo of cataclysm. Having just learned that dinosaurs still soar above us in the form of birds, your mind naturally turns to the ultimate fate of their non-avian relatives. For decades, the dominant image of their demise involved massive volcanic eruptions, spewing ash and toxic gases into the atmosphere, gradually choking the life out of the planet. It was a slow, agonizing end, a drawn-out environmental collapse. This idea of protracted volcanic activity as the primary killer of the dinosaurs is a powerful one, often depicted with dark, smoky skies and dying vegetation. But here's the next myth we're going to firmly put to rest. Volcanoes were not the primary cause of the dinosaurs' extinction. A massive asteroid impact delivered the final, devastating blow. While volcanic activity, particularly the Deccan Traps eruptions in what is now India, was indeed occurring around the same time as the end Cretaceous extinction event and undoubtedly caused significant environmental stress, it was not the sole or primary trigger for the rapid global annihilation of the non-avian dinosaurs. For a long time, the debate between volcanic activity and impact was a fierce one in paleontology. However, over the past few decades, the evidence has overwhelmingly converged on a single cataclysmic event: the impact of a massive asteroid. Imagine this: a rock estimated to be about 10 to 15 kilometers, 6 to 9 miles in diameter, hurtling through space at an unimaginable speed, perhaps 20 times faster than a rifle bullet. It strikes the Earth in what is now the Yucatan Peninsula of Mexico, creating the Chicxulub crater, a colossal impact structure over 180 kilometers, 110 miles wide. The immediate aftermath would have been beyond comprehension. An instantaneous global inferno, a massive shockwave triggering tsunamis hundreds of feet high, earthquakes of unprecedented magnitude, and vast amounts of ejected material raining back down to Earth. The heat from the re-entering debris would have ignited wildfires across continents, literally setting the world ablaze. But the real killing blow came in the long term. The impact blasted an immense amount of dust, soot, and aerosols into the atmosphere, blocking out the sun for months, perhaps even years. This impact winter plunged the planet into darkness and cold, halting photosynthesis, collapsing food chains, and leading to the mass starvation of plants and herbivores, and consequently the carnivores that fed on them. The geological record, with its sharp, distinct layer of iridium, a rare element abundant in asteroids, found globally at the KP boundary, is the smoking gun, a clear fingerprint of an extraterrestrial impact. One mainstream historical fact that solidifies the asteroid impact theory is the discovery of shocked quartz and tektites in the KP boundary layer around the world.
Shocked quartz is a type of quartz that has a unique microscopic structure formed only under the extreme pressures of a meteorite impact or a nuclear explosion. Tektites are small, glassy beads formed when molten rock is ejected into the atmosphere and rapidly cools. These distinct geological signatures, found globally at the precise time of the extinction, are nearly impossible to explain by volcanic activity alone. Now for a quirky tidbit. Some researchers have suggested that the immense energy of the impact was so great it might have literally caused the Earth's crust to ring like a bell, sending seismic waves reverberating through the planet for weeks. Imagine the entire Earth humming and vibrating from the sheer force of that cosmic punch, a geological gong sounding the end of an era. Historians still argue whether the pre-existing environmental stresses from the Deccan Trap's volcanism might have made ecosystems more vulnerable, acting as a 1-2 punch that exacerbated the asteroid's effects. While the asteroid was the primary cause of the mass extinction event, the state of the planet beforehand might have influenced the extent of the devastation. This is a subtle but important distinction. So, as you reflect on the end of the dinosaurs, don't imagine a slow fade into volcanic ash. Picture a sudden, blinding flash from above, followed by a long, dark winter that changed the world forever.
You're now moving across what looks suspiciously like a vast primeval swamp, the kind filled with murky water, gnarled roots, and the imagined stench of decaying vegetation. This is often the default setting for our dinosaur fantasies, isn't it? The idea that dinosaurs, particularly the enormous sauropods, lived exclusively, or at least predominantly, in swamps, wallowing in the mucky depths, using the water to support their immense weight. It's a comfortable, long-standing image, perpetuated by early artistic reconstructions and scientific theories that saw these giants as too heavy to support themselves on land. But here's the next myth we're going to drain. Dinosaurs did not exclusively inhabit swamps. They lived in a remarkably diverse range of habitats. Forget the pervasive image of every dinosaur, from the towering Brachiosaurus to the agile Compsognathus, being inextricably linked to a watery bog. While some dinosaurs certainly did live in wetlands and riparian environments, the fossil record now tells us a much broader story about their ecological versatility. Imagine them instead trudging across vast arid plains, scaling rocky slopes, or even foraging in dense upland forests. The Mesozoic was a time of immense geographical and climatic variety, and dinosaurs, being the dominant land animals for over 160 million years, adapted to nearly every terrestrial environment imaginable. We find fossil evidence of dinosaurs in ancient desert environments, suggesting adaptations to dry conditions, perhaps even herding behavior similar to modern-day wildebeests across dusty savannas. There's evidence of dinosaurs in polar regions, though these weren't icy poles like today, but still cold, dark for months. Imagine a hardy Leiolinosaura with large eyes, possibly adapted to low light conditions during the long polar winter, foraging for tough vegetation. This completely upends the tropical swamp stereotype. The idea that large sauropods needed water to support their weight has been largely debunked by biomechanical studies. Their robust bone structure and powerful musculature were perfectly capable of supporting their immense bulk on dry land. In fact, many sauropod trackways show them walking over firm ground, often in large herds, leaving behind clear footprints that indicate terrestrial movement, not sloppy submerged wading. If they were primarily aquatic, you'd expect their footprints to be different, perhaps showing dragging motions or a much wider splayed gait for stability in water. One mainstream historical fact that illustrates this habitat diversity is the widespread distribution of dinosaur fossils across every continent, including Antarctica. While Antarctica was much warmer during the Mesozoic than it is today, it still experienced seasons with prolonged periods of darkness.
The presence of dinosaur fossils there, including various types of ornithopods and theropods, indicates that these animals adapted to a range of climates, not just perpetually warm, swampy regions. It suggests a global distribution across various biomes, much like mammals today. Now for a quirky tidbit. Some paleontologists have even speculated about the existence of dinosaur mountaineers, species adapted to live in higher altitudes or more rugged mountainous terrain. While direct evidence is hard to come by, the discovery of dinosaur fossils in areas that were likely upland environments in the past opens up the possibility of species with stronger limbs for climbing, or perhaps unique adaptations to dealing with thinner air or rockier ground. Historians still argue whether certain groups of dinosaurs displayed greater habitat specificity than others, or if most species were generalists capable of adapting to a range of environments as climates shifted over millions of years. It's a debate about how specialized or adaptable these ancient creatures truly were. So, the next time you picture a dinosaur, don't just see it wading through a swamp. Imagine it silhouetted against a desert sunset or pushing through the undergrowth of a vast forest, a testament to its incredible adaptability across a truly global range of landscapes.
The air around you feels almost dry now, carrying the faint tang of ancient dust, a stark contrast to the imaginary swamps you've just left behind. You've navigated through diverse habitats, and as you do, your mind might still be holding onto another fundamental assumption about dinosaurs: their internal temperature. We've been taught for so long that dinosaurs were cold-blooded, sluggish reptiles, just like modern snakes or lizards, relying entirely on external heat sources to warm their bodies. This image of slow-moving, sun-worshipping giants needing to bask for hours before they could move efficiently is deeply embedded in our popular understanding. But here's the next myth we're going to challenge, a really warm one. Many dinosaurs were not cold-blooded reptiles. There's strong evidence they were warm-blooded, or at least had very active metabolisms. Forget the idea of a giant stegosaurus needing to lie inert for half the day to get its massive body up to operating temperature. The scientific consensus has been shifting dramatically over the past few decades, moving away from the purely ectothermic, cold-blooded model for dinosaurs. While the debate over whether they were truly endothermic, warm-blooded like mammals and birds, or something in between, often called mesothermic, continues, the evidence points overwhelmingly to metabolisms far more active than a typical reptile. Think about it. How could massive, active predators like T-Rex maintain their high energy needs if they were cold-blooded? How could sauropods grow to such immense sizes at such rapid rates if their metabolisms were sluggish? Growth rates inferred from bone analysis, looking at growth rings similar to tree rings, suggest that many dinosaurs grew astonishingly fast, much faster than any modern reptile, indicating a high metabolic rate that would generate internal heat. Their bones also show evidence of well-developed blood vessel networks, crucial for transporting nutrients and oxygen to rapidly growing tissues, something more typical of warm-blooded animals. Furthermore, the discovery of dinosaurs in polar regions, as we touched upon earlier, presents a significant challenge to the cold-blooded theory. While these regions weren't icy, they still experienced prolonged periods of darkness and cooler temperatures. A purely cold-blooded animal would struggle immensely to survive and thrive in such conditions without the sun to provide external heat. Their presence suggests an internal mechanism for regulating body temperature. One mainstream historical fact that lends significant weight to the warm-blooded argument is the predatory-to-prey ratio found in fossil ecosystems. In general, warm-blooded predators require far more prey to sustain themselves than cold-blooded ones due to their higher metabolic demands. Studies of fossil assemblages often show a relatively low ratio of carnivores to herbivores among dinosaurs, consistent with what you'd expect from a warm-blooded predatory population rather than a cold-blooded one.
It's like a prehistoric energy budget. Now for a quirky tidbit. Some researchers have even suggested that the sheer size of very large dinosaurs, especially sauropods, might have led to a phenomenon called gigantothermy. This means that even if they started out with a lower metabolic rate, their enormous bulk would have retained heat so efficiently that their internal body temperature would remain consistently high, essentially acting like living, walking thermal masses, regardless of external conditions. It's a bit like a giant, slow-cooling oven. Historians still argue whether all dinosaurs were uniformly endothermic or if there was a spectrum of metabolic rates across different dinosaur groups, with some being more active and warm-blooded than others. The debate also touches on whether gigantothermy played a significant role for the largest species. Regardless of the precise metabolic classification, the image of the sluggish, sun-basking dinosaur is increasingly becoming a relic of the past, replaced by dynamic, active, and internally regulated creatures. So, next time you picture a dinosaur, don't just see a cold-blooded lizard. Imagine a powerful, energetic animal radiating its own internal warmth, ready for action even on a cloudy day.
You're now moving across what feels like an ancient floodplain, the ground firm beneath your feet, hinting at open spaces. The wind, if you could feel it, might carry the imagined thud of heavy footsteps. Having just considered the internal warmth of dinosaurs, let's turn our attention to their external movements. Our popular imagination, often fueled by thrilling chases and movies, frequently casts all predatory dinosaurs as lightning-fast, relentless pursuers, capable of outrunning anything in their path. Think of a Velociraptor leaping and sprinting, or a T-Rex barreling down on its prey with incredible speed. This pervasive image of universally speedy and agile predators is a cornerstone of dinosaur thrillers. But here's the next myth we're going to slow down and examine. Not all predatory dinosaurs were speedy. Many were surprisingly slow, or at least had varied gaits and speeds. Forget the idea that every carnivore in the Mesozoic was a feathered Usain Bolt. While some smaller theropods were undoubtedly swift and agile, capable of bursts of speed to catch nimble prey, the biomechanics of many larger predators simply don't support sustained high-speed chases. Imagine a creature weighing several tons trying to outrun a gazelle over a long distance. It's simply not feasible in terms of energy expenditure or the risk of injury. Consider Tyrannosaurus Rex again. While it certainly possessed powerful leg muscles and could probably achieve respectable burst speeds, biomechanical analyses, including studies of its bone structure, muscle attachments, and even the stress limits on its bones, suggest that a full-tilt sprint might have been detrimental, risking severe injury if it tripped. Its sheer mass meant that accelerating and decelerating rapidly would have been difficult. Instead of a marathon runner, think of a powerful sprinter, capable of short, explosive bursts, but perhaps more suited to ambush tactics or overpowering prey over short distances. Its hunting strategy was likely more about brute force and surprise than sustained high-speed pursuit. This doesn't mean T-Rex was slow in the sense of being sluggish, it just means its top speed was likely far lower than the mythical 40-50 miles per hour often portrayed. Estimates vary, but many studies suggest a top speed closer to 15 to 25 miles per hour, which is certainly fast enough to catch most large, slower-moving herbivores, but not necessarily a terrifying blur. Other large predators, like some of the massive ceratopsians, though herbivores, their speed would have been limited by their bulk, would have presented a formidable challenge, relying on their defenses rather than flight. One mainstream historical fact that supports the idea of varied dinosaur speeds comes from the analysis of fossilized trackways. Paleontologists can analyze the spacing and depth of footprints to estimate the speed at which a dinosaur was moving.
These trackways often show a range of gaits, from slow walking to moderate trots, but rarely the kind of high-speed sprinting that popular culture depicts for the largest dinosaurs. For example, some sauropod trackways indicate a surprisingly leisurely pace, perfectly suited for their grazing lifestyle. Now for a quirky tidbit. Some paleontologists have even suggested that the unique gait of certain dinosaurs, particularly those with long, heavy tails, might have involved using their tails as a dynamic counterbalance during movement, swinging them side to side like a pendulum to aid stability and propulsion. This would create a distinctive, perhaps even rhythmic lumbering motion rather than a smooth, effortless sprint. Historians still argue whether the presence of smaller, faster-running theropods in ecosystems influenced the evolutionary trajectory of larger, slower ones, forcing them into different hunting strategies or relying more on ambush. It's a debate about the ecological pressures that shaped dinosaur locomotion. So, the next time you envision a dinosaur chase, don't just see a single terrifying blur. Imagine a spectrum of speeds and strategies, from the quick dart of a small hunter to the powerful, deliberate stride of a giant, all moving at their own unique pace through the ancient landscape.
You're now moving into a clearing, perhaps near a towering cliff face, and instinctively, your gaze turns skyward. You might imagine giant, leathery wings beating against the ancient sky, casting vast shadows on the ground below. When we think of airborne creatures from the age of dinosaurs, a single image often dominates: the enormous, soaring, flying dinosaurs. We've been taught to lump all large, ancient flying reptiles under the umbrella of dinosaurs, especially iconic ones like pterodactyl, a common, though often misused term for all of them. This common misconception places these magnificent flyers squarely within the dinosaur family tree, soaring alongside their terrestrial cousins. But here's the next myth we're going to clearly delineate. Pterosaurs, the winged reptiles of the Mesozoic, were not dinosaurs but close evolutionary cousins. Forget the idea that the sky was just another domain for dinosaurs to conquer. While dinosaurs ruled the land, and eventually, through birds, the air, the first true masters of Mesozoic flight were a distinct and equally fascinating group of reptiles known as pterosaurs. They were the contemporaries of dinosaurs, sharing the same landscapes and skies for millions of years, but they belonged to a separate branch of the Ichthyosaur family tree. Think of it like this. Humans and chimpanzees are both primates, sharing a common ancestor, but they are distinctly different species. Similarly, dinosaurs and pterosaurs share a common reptilian ancestor, but they evolved along separate paths. Pterosaurs, such as Pteranodon with its massive wingspan and distinctive crest, or the truly enormous Quetzalcoatlus, the largest known flying animal to ever exist, were truly spectacular creatures. Their wings were formed by a membrane of skin, muscle, and other tissues stretching from a vastly elongated fourth finger to their ankles. This is fundamentally different from the wings of birds, which are modified forelimbs with feathers, and bats, which have membranes supported by all 5 elongated fingers. This unique wing structure is a key anatomical difference that clearly separates them from dinosaurs. They filled a vast array of ecological niches in the air, from fish eaters skimming over ancient seas to insectivores snatching prey in mid-flight, and even terrestrial stalkers that hunted on the ground. Their diversity in size and form was astounding, ranging from sparrow-sized species to giants with wingspans rivaling small aircraft. They were the dominant aerial vertebrates of the Mesozoic, a testament to their own successful evolutionary story parallel to that of the dinosaurs.
One mainstream historical fact that distinguishes pterosaurs from dinosaurs is their unique post-cranial skeletal features beyond just their wings. Pterosaurs had hollow, air-filled bones, but their overall skeletal structure, including their pelvis, shoulder girdle, and limb proportions, were distinct from those of dinosaurs, reflecting their adaptations for flight. They also possessed unique features like a notorium, fused dorsal vertebrae for rigidity during flight, and a pteroid bone to support the leading edge of their wing membrane. These are not found in dinosaurs. They filled a vast array of ecological niches in the air, from fish eaters skimming over ancient seas to insectivores snatching prey in mid-flight, and even terrestrial stalkers that hunted on the ground. Their diversity in size and form was astounding, ranging from sparrow-sized species to giants with wingspans rivaling small aircraft. They were the dominant aerial vertebrates of the Mesozoic, a testament to their own successful evolutionary story, parallel to that of the dinosaurs. One mainstream historical fact that distinguishes pterosaurs from dinosaurs is their unique post-cranial skeletal features beyond just their wings. Pterosaurs had hollow, air-filled bones, but their overall skeletal structure, including their pelvis, shoulder girdle, and limb proportions, were distinct from those of dinosaurs, reflecting their adaptations for flight. They also possessed unique features like a notorium, fused dorsal vertebrae for rigidity during flight, and a pteroid bone to support the leading edge of their wing membrane. These are not found in dinosaurs. Now, for a quirky tidbit, some paleontologists have suggested that the elaborate head crests seen on many pterosaurs, like Pteranodon, weren't just for display or species recognition. They might have also served as rudders for steering during flight, or even as heat radiators to help dissipate excess body heat during strenuous activity. Imagine a magnificent Pteranodon not just flying, but subtly adjusting its course with a graceful tilt of its cranial sail. Historians still argue whether pterosaurs and dinosaurs evolved flight independently multiple times, or if the genetic predispositions for flight-related features, like hollow bones, were present in a common archosaur ancestor. This debate explores the deeper evolutionary pathways that led to such incredible aerial diversity. Regardless, it's crucial to remember that while they shared the same ancient skies, and often the same habitats, pterosaurs were not dinosaurs. They were their own distinct, incredibly successful lineage, conquering the air millions of years before their bird dinosaur cousins truly took wing.
You are now standing at the edge of a vast, ancient sea, the air thick with the tang of salt and the distant cry of primordial seabirds, which, as you now know, are dinosaurs. You watch the imaginary waves lap against the shore, and your mind likely conjures images of immense reptilian forms gliding through the depths. When we think of prehistoric sea monsters, we often instinctively label them as marine dinosaurs. The very phrase rolls off the tongue. Aquatic dinosaurs, conjuring images of titanic creatures like Mosasaurus or Plesiosaurus as ocean-dwelling cousins of T-Rex. This widespread belief puts all the large, awe-inspiring reptiles of the Mesozoic in the same family, whether they lived on land, in the air, or in the sea. But here's the next crucial distinction we're going to make. Marine reptiles like Plesiosaurs and Ichthyosaurs were not dinosaurs. They were distinct lineages that adapted to oceanic life. Forget the idea of a comprehensive dinosaur family that included every large reptile from every environment. While dinosaurs certainly ruled the land and pterosaurs the skies, the vast oceans of the Mesozoic era were dominated by several different groups of marine reptiles that evolved entirely independently from dinosaurs. They were magnificent, awe-inspiring creatures in their own right, perfectly adapted to their watery world, but they were no more dinosaurs than a modern-day whale is a cow. Take the Ichthyosaurs, for example. With their sleek, fish-like bodies, powerful tail flukes, and long snouts filled with teeth, they were the Mesozoic equivalent of dolphins or tuna,
perfectly streamlined for pursuit hunting in open water. Their evolutionary journey saw them move from land-dwelling reptiles back into the sea, developing an incredibly convergent body plan with modern fish and marine mammals. Then there are the Plesiosaurs, with their often long necks, stout bodies, and 4 powerful flippers. They ranged from the short-necked, powerful pliosaurs like Kronosaurus to the classic long-necked forms. They swam with a unique underwater flight motion, using their flippers like paddles, similar to modern sea turtles. And of course, the fearsome Mosasaurus, a giant, predatory lizard closely related to modern monitor lizards like the Komodo dragon, but adapted for marine life with paddle-like limbs and a powerful tail. These groups, despite their superficial resemblance to dinosaurs in terms of being large, extinct reptiles, had fundamentally different skeletal structures, evolutionary histories, and anatomical features. Dinosaurs are defined by very specific hip and limb structures that allowed them to walk upright with their legs directly beneath their bodies, unlike the sprawling gait of most other reptiles. Marine reptiles, on the other hand, had limbs modified into flippers or paddles, and their hip and shoulder girdles were adapted for swimming, not weight-bearing on land. One mainstream historical fact that underscores this distinction is the fossil record itself. The earliest true dinosaurs appear in the Triassic period, evolving from a specific lineage of archosaurs with adaptations for upright posture. Marine reptiles, on the other hand, have their own distinct evolutionary origins, with many groups appearing earlier or diversifying separately from the dinosaur lineage. For example, Ichthyosaurs likely evolved from a group of land reptiles in the early Triassic, millions of years before the Great Dinosaur diversification. Now for a quirky tidbit. Some ichthyosaur fossils have been found with embryos inside them, showing that they gave birth to live young at sea, rather than returning to land to lay eggs like sea turtles. This is a remarkable adaptation for a reptile and further highlights their complete commitment to a marine lifestyle, unlike any known dinosaur. Imagine a prehistoric midwife assisting with a live birth in the deep ocean, far from any land. Historians still argue whether the dominance of marine reptiles in the oceans placed any evolutionary pressure on land-dwelling dinosaurs, preventing them from significantly adapting to marine environments, or if their terrestrial specializations simply made such a transition less likely. It's a debate about ecological partitioning and evolutionary constraints. So, the next time you picture a colossal creature of the ancient deep, remember its proper lineage. They were magnificent, yes, but while they swam alongside the age of dinosaurs, they were never truly dinosaurs themselves.
You're nearing the end of your ancient journey, the imaginary ocean air now fading, replaced by the soft sounds of a rustling breeze. We've explored the truth behind their forms, their lives, and even their surprising persistence in the form of birds. And as you prepare to settle into a deep slumber, your mind might conjure the classic sound of a dinosaur, a guttural, earth-shaking roar, like something out of a primeval nightmare. It's the sound we've all heard in movies, the iconic bellow of a T-Rex echoing through the jungle, signaling terror and power. This pervasive image of dinosaurs primarily communicating through thunderous roars is deeply ingrained in popular culture. But here's the final myth we're going to whisper away tonight. Dinosaurs likely didn't just make loud roars. Their vocalizations were probably far more varied and often much quieter. Forget the singular, terrifying roar as the definitive dinosaur sound. While some large dinosaurs might have produced deep, resonant calls akin to the rumbling of modern alligators or the low-frequency vocalizations of elephants, the anatomical evidence suggests a much broader soundscape for the Mesozoic. The idea of a universal dinosaur roar is largely a cinematic invention designed for dramatic effect rather than scientific accuracy.
Consider the anatomy of a dinosaur's throat and vocal cords. Unlike mammals, which have complex vocal cords, or birds, which possess a unique vocal organ called a syrinx, most reptiles have simpler laryngeal structures. This suggests that while they could likely hiss, growl, or make deep rumbles by expelling air, they probably couldn't produce the complex, sustained roars we often associate with them. Think about a modern crocodile or alligator. They produce low-frequency bellows, especially during mating season, sounds that can travel far through water and ground, resonating more than projecting outward. It's an infrasound, a deep vibration you feel more than hear with your ears. Furthermore, many paleontologists now believe that some dinosaurs, particularly feathered ones, might have made sounds more akin to their bird descendants. Imagine cooing, clucking, chirping, or even hooting. Small feathered dinosaurs, perhaps living in flocks, might have communicated with a variety of chirps and calls, signaling danger, identifying each other, or coordinating movements. The sounds of the ancient world might have been a symphony of varied calls, from the deep rumbles of giants to the high-pitched trills of smaller bird-like creatures. Some dinosaurs might have even had resonating chambers in their crests or nasal passages, allowing them to produce unique trumpeting sounds, much like a cassowary or a hadrosaur. One mainstream historical fact that supports the idea of varied dinosaur vocalizations is the study of hadrosaur crests. Many hadrosaurs, or duck-billed dinosaurs, had elaborate hollow crests on their heads. By creating casts of these nasal passages and using computer models, scientists have been able to reconstruct the sounds these dinosaurs might have made. The results suggest sounds more like deep honks or trumpeting calls, not unlike a trombone, rather than a roar. These crests likely acted as resonance chambers, amplifying and shaping specific calls for communication within their herds. Now for a quirky tidbit. Some researchers have even speculated that certain dinosaurs might have communicated using infrasound, frequencies too low for the human ear to perceive, much like elephants do. This would allow them to send messages over vast distances through dense forests without alerting closer predators or prey that weren't sensitive to those frequencies. Imagine a deep, silent conversation rippling through the ancient landscape, felt in the ground more than heard in the air. It's a subtle, almost eerie thought that these giants could be talking right past you. Historians still argue whether the evolution of complex vocalizations in birds was a relatively late development in dinosaur evolution, or if many non-avian dinosaurs possessed a greater capacity for varied sounds than current fossil evidence suggests. The debate often centers on the limitations of inferring soft tissue structures like vocal cords from skeletal remains. Nevertheless, the era of the universal dinosaur roar is fading. The true soundscape of the Mesozoic was likely far richer, more subtle, and in many ways more complex than we ever imagined. As the final echoes of these ancient revelations soften, feel the stillness settle around you. The colossal forms and roaring giants begin to recede, not into oblivion, but into a tapestry woven with newfound understanding. Those myths, those comforting, familiar inaccuracies, they gently dissolve, replaced by a world far more intricate, more vibrant, more subtly alive than you ever dared to dream. The ground beneath you isn't just prehistoric Earth, it's a silent testament to countless generations, to adaptations and struggles, to life's relentless dance through eons. And those tiny rustlings you imagine, they're not just shadows, but the whispers of creatures, large and small, some of whom still flutter and sing in the trees just beyond your window. The past isn't truly gone, it merely transforms, echoing in the wings of a bird, in the deep rumbles of the earth, in the quiet wisdom you now carry. Let the echoes soften, let the incredible scale of time and evolution wash over you, and let your mind drift into the peaceful quiet that only true understanding can bring.